Okay, so we're in chapter 13, section 4, and we recall that in section 3, we talked about the rate law, right? Rate law, where rate is equal to K times the concentration of some reactant raised to some order, which we called N or M or X or whatever, okay? So this was an example of a rate law. And what we're going to do now is we're going to talk about the integrated rate law. And this is really interesting. The reason why the integrated rate law is interesting is because it enables us to think of things in time in terms of t. Can you see t right there? So this was an example of a rate law. And then suppose rate law was 1. If rate law was 1, we would use some calculus to integrate like it's done in the margin of page 529, in case you're interested, page 529, and we would find that, do you remember now that rate, right, of course, is the change in some concentration over, how do you spell delta? Change in T, right? That was the rate, and it would be negative if it was disappearing. So that was the rate. Well, if we were to take that and we were to solve for t, this is what we would get down here. This would be our integrated rate law. And that is the integrated rate law for a first order reaction. First order reaction, okay? We're going to see this again, but I mostly wanted to take this opening slide and orient you to what we're talking about. In section 13.3, we have the rate law, which was rate. I know I'm saying this over and over again, but I think it's worth repeating. And in 13.4, we have the integrated rate law. Integrated rate law. Boy, my handwriting is going to heck, isn't it? Integrated rate law. All right, and that's got lots of different forms, so I don't want to have a general form there for it. But here's one of them. This is an integrated rate law. Integrated rate law right there. All right, so we find with the zeroth order, we had the rate law was, remember that? Rate, I'm going to try to go real slow and make my handwriting nice, K to the 0, right? Which is the same thing as K, because that was just 1, right? That just goes to 1. So that was the rate law, but the integrated rate law is here. It is the concentration of the A at some time t, at time t, whatever that number is, it's this t, right, is equal to minus K, and that's the same K as this, right? Minus K times the time plus the initial concentration. That's what that means. That's the initial concentration, okay? And we call it, some people call it A0. I think I don't even know what I call it. I hear people talking about it and they go, oh, this would be read, the concentration at time t is equal to minus KT plus the concentration A0. All right? Now the first order integrated rate law, remember the rate law for the first order? It was rate is equal to K A to the 1, right? Which is really just K concentration A. Remember that? I'm not doing very good with my handwriting here, am I? So the integrated rate law for that is this, the natural log, that's ln, of the concentration of A at time t, that t, is equal to minus KT plus the natural log of A0. And look at how similar these two integrated rate laws are. They look very similar. This is just the natural log of those two terms. Uh-oh. This second order rate law, I did not get this right. The first order is correct, but I got a mistake here. This is not the second order rate law. Okay, I'm looking it up right now. It's really, this is wrong. Nah, it's really 1 over A at time t is equal to positive kt plus 1 over A0. Okay? Sorry about that. All right, so we're gonna, you'll have these on a table. The last thing we do for this talk is to remind you of what these rate laws are. So, I mean, a great thing to write down. You have them in your worksheet there. The worksheet that I provide with this video, I recommend that you write those down. But they are, now we're going to practice some, right? So what do you expect the practice to be? Well, I'm going to give you time t and k and A0 and ask you what AT is. Or I'm going to give you AT minus k and A0 and ask you how long it took, right? That's how these are going to look. That was an accident. That was an accident. All right, so that's how these practice problems are going to look. Before we do that, let's think about this for a second. Tro and a lot of scientists on page recommend that you consider this. He does this on page 30. 530, okay? So Tro says, all right, this is a really valuable and powerful tool for scientists. Try to think about how we can find important information graphically. All right, so what we're going to do is we're going to think about the integrated rate law for a first order reaction. Okay, and it is, remember, now, well, you've got it written in front of you. You don't have to remember it, right? You will eventually need to remember it, but for now, natural log is equal to minus kt plus, is that right? Let me just look at over here, my shoulder. That's right, plus the natural log of the concentration of A at time 0, right? So notice this, that if I graph mx plus b, if I graph a first order reaction time, this is my x-axis, and my y-axis I do to be ln AT, right? Can you see that? Look at that. Ln AT. This is my y-axis, right? If I graph ln AT per time, then I can find k just by evaluating the slope. Look at that. Well, it's negative k, right? You see that? I can find that the slope here now is just going to be minus k, because look at that. There you go. That's the reason I do that. All right? And I can also find what is the y-intercept. Of course, it's going to be the natural log of A0. Can you see that? This is not unique to reactions. Okay, a lot of chemistry procedures are evaluated in this way. It's a super powerful tool, and I want you to see it. All right, so let's look at a problem. I think the first problem we're going to look at here is example problem 13.2 on page 527. And it looks like this. Consider the equation for the decomposition of blah, 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 right? So we've got SO2Cl2 produces blankety blank and such, okay? Now, can you see that I only have one thing that's breaking down here? It's SO2Cl. So, you know, in the previous language, I was calling that A, right? Well, there's the concentration of SO2Cl2. And that's it right there. So this is like my concentration of A, right? And here's my time. Okay, so what I'm supposed to do, first of all, is show that the reaction is first order, and then determine the rate constant for the reaction. Okay, so the way I'm going to do this is I'm going to say, all right, well, if it's first order, and I've got times, you see I've got times here, I'm going to use the integrated rate law. I'm going to use the IRL, the integrated rate law. And I know my integrated rate law, again, is natural log of A at time t is equal to minus kt times the plus the natural log of A0, right? Okay, so this says using graphical analysis of reaction data. I'm gonna tell you what the graphical looks like, but I'm gonna solve it without graphical. I'm gonna make it a little bit simpler. So first of all, before I do that, I'm gonna set up a separate column here, and I'm gonna have to do it right here because it didn't give me room. It didn't give me room in the, right? So I'm going to say this is, if that's A, let's do the limit of A at time t, right? So the limit of A at time t is, first of all, and I've got to get a calculator here, and I'm going to say 0.10 in my calculator, or rather natural log of 0.1. Natural log of 0.1, and that is, just a second here, natural log, 0.1 natural log. My calculator's got to go backwards, okay? So this goes to be negative 2.3, okay? Now I'm going to do the natural log of 0.0971 natural log, and that goes to be minus 2.3. This was really 2.30. Can you read my writing? You should be doing the same thing, okay? So what's the natural log of 0.0944? 0.0944 natural log. Do it in your calculator. Pause the video and see if you can keep up with me. Minus 2.36, okay? Well, if it's first order, I don't have to do all of them. I'm just supposed to show that it's first order, okay? So the way I'm going to show it's first order is I'm going to show that if I graph, let's do 4 points here, okay? 0.0917 natural log goes to minus 2.39, okay? So what I'm going to do in order to show its first order is I'm going to graph, you know what I'm going to do? I'm going to go to a different color here. Just spice things up a little bit. Keep you guys guessing. Natural log of A times T, right? That'll be my Y. And that'll be my X. And that will be my, well, y-intercept, right? Okay, and what's my slope? It's minus X. Oops. Minus K, sorry. Crud. I see I don't have an eraser with this marker here, so my slope is that, right? So let's let T be my x-axis. Man, my handwriting is just awful today. Honestly, folks, usually it's beautiful. Okay, if you don't believe me, just ask my mother. So let's say here's 0. How do you spell 0? With a 1. And here's 100, 200, and 300. Those are the only ones I calculated, okay? So let's go here and say that at 0, it's minus 2.3. Okay, I got to think about how I'm going to graph these guys. You know what I'm going to do? I'm going to assume if you did this with a Excel, you would see that it comes out beautifully, okay? But I'm going to graph these by hand, and you're going to take my word for it. This is a minus 2.3. That's minus 2.33. You know what? I need to give myself enough spaces here. That's minus 2.3, minus 2.33 here, minus 2.36, minus 2.39. Actually, you can see that these are evenly spaced, right? 30, 33, 36, 39. Those are evenly spaced. So it looks like the first point here, here's my time, here's my natural log of AT is 0, right? And my next one is here, right? There's my time, and here's my minus 2.33. Do you see my 100? This is in seconds. Okay, the next slide, my handwriting is going to be beautiful. Okay, that's my pledge to you, my solemn vow. Right? Minus 2.36, can you see that? At 200? Okay, and so if I'm supposed to show its first order, then I use a first order integrated rate law, and I graph it, and then I say it's linear. Okay, so I have shown that it's first order. Okay, I'm going to say QED. quod erat demonstrandum, which I don't know if I'm pronouncing that right, but that's Latin for that which was to have been demonstrated. It means I'm done. I'm good. Stars. Give me a star. Now, determine the rate constant. So the rate constant is going to be the slope of this guy, right? So what's the slope? It looks like these are even. So the slope is, it looks like it's, well, I don't know. Slope is equal to rise over run, right? Which is y2 minus y1 over x2 minus x1. I can't do this in my head, so I've got to do this, okay? Okay, so y2, it doesn't matter which one I choose, of course, right? So let's let this be, this was my x, and this was my y, right? So let's let this be my first point, and this will be my second point, okay? So my y2 is going to be minus 2.33, minus 2.33, and my y1 is minus 2.30, okay? And my x2 is 100, and my x1 is 0, okay? This is going to be something over 100. So what's minus 2.33? It looks like it's minus 0.03, okay? Over 100, wow, okay. So this looks like it's minus 3 times 10 to the minus 4. That's what that is. That's what K is. Minus 3 times 10 to the minus 4, okay? So, looking here at my notes, minus 3 times 10 to the minus 4. Just 1 second here. Checking my notes out to make sure I'm not getting too far afield. And it says 13.4. Yep. Okay. Minus 3 times 10 to the minus 4. All right. Now, and that's what my K is. K is equal to minus 3 times 10 to the minus 4. All right, and that's just using these two points right here, 1 and 2. We would, if you wanted to prove this to yourself, if the pressure was on and you really wanted to make sure you got this question right, you can use a couple different points. Calculate the natural logs of those to get your y and your x over here. Make sure you get the same thing, and sure enough, that's going to demonstrate that it's also going to demonstrate it's first order. All right, so that said, there's my answer for my second part. Here's my answer for my first part, which includes that graph, and I'm done with this problem. Oh, you know what? I do need to put the units in here, sorry. So if it's first order, then my rate, watch this, rate is equal to Ka. So my rate is going to be in molars per second, right? That's how rates are. And this is going to be in molars, right? My concentration of A is, and so this must be in reciprocal molars per second. And that'll give me, wait. No, just reciprocal seconds, right? Can you see that? That'll give me molars per second. So this is going to be in reciprocal seconds. That's the unit for K. All right. So let's move on and talk about, let me go back and look at first order reactions again. So, question 13.4 is now, okay, so you determine the decomposition of SO2, Cl2 under the given reaction conditions is first order and has a rate constant. Oh, I said minus, but it was minus K. Crud. And my notes are gone, so you won't be able to tell. I'll go back here. But remember, look at this. I said, I got that wrong. I said in my previous question, rate is equal to K. Oh, my integrated rate law was natural log of A at time t is equal to minus KT plus natural log of A at time 0. What I did was I solved for minus K and called it minus 3 on the previous slide. But really, remember this was mx. So the slope was minus 3, but K is the minus of that, right? So it should be plus 2.9 times 10 to the minus 4 reciprocal seconds. Okay, so hopefully you caught that, but if you didn't, you might want to go back and look at that again. All right, so we find that it has a first order rate constant of such and such. If the reaction is carried out at the same temperature, in other words, K, that means right there, K is the same, because K is a function of temperature, okay? Carried at the same temperature, the initial concentration of SO2Cl2 is 0.0255 molar. What is that after 865 seconds? T is equal to 865 seconds. All right. So what we need to do then is take our integrated rate law, because it's a time. It's a they're giving us a time. And so we're using the integrated rate law, not about rate, it's that. And if that's the case, then what I'm going to do is I'm going to take my integrated rate law, and I'm going to change colors now to keep things clear. And I'm going to say the natural log of A at time t is equal to minus kt plus the natural log of A0. So what's being asked here? What is the concentration at time t? That's what's being asked, and not the ln of that, but that, okay? So in order to solve this, I'm going to raise both sides to the e, and I'm going to find that this is going to be e raised to the minus kt plus the natural log of A0. Okay? So that's how I solve for A at time t there. Now let's go ahead and work this out little by little. E minus, which is 2.9 times 10 to the minus 4. I'm going to leave the units off for now. Times, but it was in seconds. You see reciprocal seconds here, and this is also in seconds. Times 865 seconds plus the natural log of 0.0225. My handwriting's neater in this, isn't it? You can see it. Okay, so this is E. And I'm going to go ahead and solve this one step at a time. 2.9 times 10 to the negative 4. Just a minute here. Two point nine. Wait. 2.9 times 10 to the minus 4 times 865 equals 0.25085. 0.25085 plus the natural log of 0.0225, and that's natural log of that is minus, minus 3.7942. Okay, you can see it'd be easy to get this wrong just by not being careful, okay? So I'm going to go ahead and add these two first. Plus 0.25085 equals minus 3.5434. That's equal to e to the 3.5434, which is equal to, okay, I'm going to be done. The concentration of A at time t is equal to, all right, just a moment, please. I got to make sure I got this in my calculator right. E to that number, 34.54. And that is wrong. Ah, this is where I got it wrong. I'm looking at my notes here. This. That minus goes with that. Crud. Okay, so this is wrong. But you go through and work this again, all right? Do you see how I got the minus wrong there? This was wrong because I got the minus on that. And this minus times 865, this should not be in parentheses. That minus should be right there. That minus should be right here, okay? So that makes this turn out to be minus 4.04. All right. So you know what I'm going to do? I'm going to leave this. I'm going to show you that how easy it is to make a mistake. I'm not even going to re-record this portion of the video. You got to know if you don't get those things right, and that was an accident on my part. Okay, it wasn't. I'm not playing games with you here, but I would have gotten that one wrong. So all right. Well, I mean, it sort of depends on how careful I was being. Maybe I wouldn't always get it wrong. Sometimes I get that. Usually I'll get that right, but in this case, that was an honest mistake. Okay, let's move on to the next point. I want to go now, though, and go back to first-order reactions and remind you that with first-order reactions, if our rate law, or our integrated rate law, the integrated rate law is the natural log of A at time z, or rather time t, is equal to minus k at time t plus the natural log of A at time 0, right? That's the integrated rate law for a first-order reaction. Okay, we can set this up as y is equal to mx plus b, where y, my y-axis could be that, my x-axis is time, and the slope of the graph then is going to be minus k. Man, that's two mistakes I've made here in this demonstration. I'm going to leave them. I'm going to let you guys see that. It's real easy to make these mistakes. Your minuses, you've got to, and both of them were with a minus sign. Both of my mistakes were. All right, and then your y-intercept, of course, is going to be this over here, which we haven't really worked with here, but that's your y-intercept. You see that? Okay, so let's do the same thing for, I think, a zeroth order reaction or second order. Okay, let's do second order. Remember now that the integrated rate law, remember, or look at your notes. I wouldn't expect you to remember it, I guess. Let me go back to red for a second. Red. The integrated rate law is 1 over the concentration of A at crud. Okay. Red, still red. Okay. Remember that the integrated rate law for a second order reaction is 1 over A, concentration of A time T is equal to positive KT I'm just looking at my notes. I don't want to get this wrong again, okay? Positive KT plus 1 over A 0, right? Which is the initial concentration of A. Now, you might say to yourself, how can we make this linear? Oh, well, it's set up linear already. Look at that. If I graph, and this is going to be the solution to sometimes it's the problem. They'll say, all right, show that it's second order, show that it's first order. Well, you take the integrated rate law, and you set that up as your y, right? So you have to calculate the reciprocal of the concentration of A at time t. And then let that be your y-axis, right? And then mx, and you're letting time be your x-axis, right? And your slope then, in this case, is going to be k, right? You see that? And that's what this is about. Okay, so let's do the same thing for zeroth order. And actually, I want you pause the video right now and predict where we're going with this. It's in your book, but and you should have your book out, right? But suppose that you try not to look at your book for a second. Look at the integrated rate law for zeroth order and decide what are we going to graph against what. What is going to be the y-axis and what's going to be the x-axis? Okay, let me suppose you did that. like I asked you to, and I'm gonna come over here and say red. Let's go red again. The integrated rate law for zeroth order, IRL, for zeroth order is going to be the concentration of A at time t is equal to minus KT plus the concentration of A initial, right? So can you see that? See what we're doing here? This is awesome, isn't it? We're going to, where's blue? We're going to let this, right? Can you see I've got a linear form here? So we're going to let the y-axis be the concentration of A at time t, the x-axis be t, right? And my slope is going to be minus k again. And my y-intercept is going to be there. All right, so let's do, I think, one more problem here. All right, you know what? This one's a long one. This is a beast. All right, so look at this. The second order reaction using graphical analysis. Consider the equation for the decomposition of nitrogen dioxide, okay? And then they're saying, all right, show by graphical analysis that the reaction is not first order and it's second order instead, okay? Well, in order to do that, I really don't want to take the time to graph all this out. The way we would do it is we would say, I'm gonna lose these notes. These are temporary notes here. I would say, remember that first order is natural log of A at time t is equal to minus KT plus the natural log of A at time 0. And a second order is 1 over, right, KT plus 1 over at time 0. So what we would do is we would figure out, we would set up a column over here for the natural log of A, and that would go here. And we would set up another column for 1 over A t, right? And that would go here, right? And then we would graph them against time. We would graph both of them against time and see which one was linear. If this one was linear, well, we're supposed to here show that this is not first order, so we're expecting this is not going to be linear. What does that say? Hot linear? Okay, so if we graph, here's my x. If we graph x against this y, that y right there, it's not going to be linear. If we graph this x against this y, I'm going to call that y prime. If we graph x against this column here, this column against that column, we'll find that it is linear, and that's because it's second order. That's how we're going to show by graphical analysis that it's second order. Let me do that with you. I'm going to, I think almost all, and then determine the rate constant for the reaction. Okay, so let's come back here. We're going to have to do that in the end. But I'm going to come over here. My computer's a little bit busy here, so you have to bear with me. All right, so I've put in some of the first ones here, right? I've just put in the first, oh, I don't know. Yeah, the first bunch, okay? Roughly first half. So let me set up this here, and this was for the first order. For first order, this is going to be 1 over, or rather, the natural log of the concentration of A, right, at time t, okay? And for second order, can you see what I'm writing on my screen? This is going to be 1 over A at time t, okay? So here's what I'm going to do. I'm going to say this is equal to, watch this, you're going to love this, natural log, bam, okay? And this is equals 1 over, bam, right? And now I can calculate both of these at the same time. Just a minute here. Okay? So now for first order, x, y, and I'll do it for second order over here, x, y, okay? So for this x, I want that to equal that, boom. And for this y, I want it to equal that, boom. And let's take these first few ones, okay, and let's graph this. Now I'm going to take that and graph it. If you're not familiar with Excel, this is probably a little bit overwhelming. You could do this by hand. It would just take a long time. And I don't want to take that much time for it. I'm not sure that would be helpful. So I'm looking for a chart. Boom. Scatter. Boom. Watch this. Okay, can you see that that's not linear? All right, let's add a trend line. Add a trend line, and you'll see that the line does not, look at that, the line does not lay on top of that. So no, that is not linear. Do you see how these points don't go on there? Okay, well let's do this. I'm gonna get this graph out of the way here. Now let's come over here and let, for second order, that'll be my x, and that will be my y. That's my second order right there. Boom. Okay. Now let's take those and graph those. Insert, graph, scatter. Watch this. This is going to be gorgeous. Because we know it's second order, right? They told us. And the question said, show that it is second order. It assumed it was linear. Look at that. And can you see that if I do a trend line, those all lay right on top of there? Now look at, this is the nice thing about Excel, is I can just display the equation on the chart, and there's my slope right there. Boom. You see it? So my slope is 0.2547. Can you see that from where you're sitting? It's probably pretty small, isn't it? Let me see if I can make that font bigger. Format, text box, font, 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 font. Come on, font. Let's go. Don't have all day. Format. Oh, come on, come on, come on, come on. Trains. Yeah, let's try. No, yeah, let's try that. All right, I can't do it. All right, so I'm not familiar with this this version of Excel. Text options, text fill, label options. I know. If you're familiar with Excel, it's probably killing you to see me do this. All right, so anyway, the slope here says 0.2547. 0.2547. So let's go back to our PowerPoint, and we'll find that the slope, just a minute here. Oh, you know what? I'm not in presentation mode. Just a minute here. Go back to presentation. Oh no. Please give this back to me. No, cancel. Presentation mode. Let's go back here and say that the slope, what was the slope? 0.2. Oh no, I forget. Gotta go back. Be right back, folks. The slope was 0.2547. Should have written that down. You write it down next time, and then I'm going to ask you in just a second. You tell me what it says. 0.2547. Presentation mode. Pen. Slope is equal to what? 0.2, I heard you, 2547, okay? And we know that the integrated rate law for a second order reaction that's a K. KT plus 1 over, and you know this because you're looking at it on your notes, right? 1 over the concentration of 8 times T. All right, and so it looks like my slope, Y. Okay, so it looks like my slope is K. I'm pretty sure I got my negatives right this time. It was a graph. Remember, the graph was going up like that. That's a positive slope. And K is positive, so K is going to be 0.2547. And the units for a second order one, let me think about this for a second. If rate is equal to K, A squared, which is equal to molars per second, because that's what rate is, molars per second, is equal to K times molars squared, because that's what this is, right? So this must be, so K, this implies that K is going to be 1 over molar seconds. Okay, so your book probably says molar seconds. That's probably how that's given. Okay, so there's the answer. Was that what I was supposed to do? Determine the rate constant. Yeah, and then we were supposed to, first of all, we were supposed to do show by graphical analysis that the reaction is not first order, which we graphed it and it was not in the line, and it is second order and it was linear, and then we found the slope and it was K is equal to that. All right. I like to write QED at the end here. QED, because it sounds so small.